Hey everyone, this is a continuation of our third lecture on groups. The last one just sort of stopped on its own, so we're continuing. You might remember in the last lecture where we stopped that we had two different groups having four elements each, uh, but they weren't the same group with the elements just named differently. They were structurally different. Nevertheless, even though they were structurally different, they did have something in common algebraically. The binary operation was commutative, and we could tell by looking at the group table that the binary operation was commutative just by examining entries on either side of the main diagonal. If we take an entry in the table and look at its mirror image across the main diagonal, and they're the same element for all pairs of corresponding elements, then the operation is commutative. So in other words, if we pick an element in row 3, column 2, and then we pick its mirror image across the main diagonal, row 2, column 3, and the elements are the same in every case, then the operation is commutative. Let's look at a case where we have a group of three elements. Here's the main diagonal. And let's look at pairs of elements. Elements with their mirror image. Okay, they're the same. Row A, column E, and row E, column A, they're the same. Let's look at this pair. Row B, column E, and row E, column B. And finally, row B, column A, and row A, column B. The elements, as we look at them across the main diagonal, all pair up. If we take an element below the main diagonal and match it up with its counterpart, it's the same element. If we take an element below the main diagonal and match it up with its counterpart above the main diagonal, same element in every case. So that tells us that the operation is commutative, or we could say the group is abelian. So in a group with three elements, the operation is commutative. The group is abelian. In a group with five elements, well, I don't know. But we looked at four elements, and with the groups that have four elements, the operation is commutative. Let's check out this example with a group of five elements. And we'll go right down the main diagonal. And we'll take one element below the main diagonal and match it up with its counterpart above the main diagonal. They're the same. Take an element below the main diagonal, match it up with its counterpart above the main diagonal. They're the same. Take an element below the main diagonal, it matches up with its element above the main diagonal. Take another element below the main diagonal, match it up with its counterpart above the main diagonal. They're the same. And let's see, we can match these two up. They're the same. We can match these two up. They're the same. And then these two, same. These two, same. Whoops, whoops, whoops. What did I just do? I must be hard of thinking. Well, that's what happens when you fly on autopilot. Yep, let's try that again. Okay, take an element below the main diagonal, and I guess I want to use blue here, don't I? An element below the main diagonal, the corresponding element above the main diagonal, they're the same. Take an element below the main diagonal, its counterpart above, they're the same. An element below the main diagonal, one above the main diagonal, they're the same. So in each case, if we take an element, let's say in row C in column A, and match it up with the corresponding element in row A in column C, same element. And that happens for all ordered pairs. The table is symmetric about the main diagonal. So again, star is commutative. Or we could say the group is abelian. There's something else that we can take away from these examples as well. If you go back a bit to the two examples where we had groups with 4 elements, you'll find that this was true in the case with groups that had 4 elements. We can see that it will be true with the groups that we have of 3 elements and 5 elements. And what I'm talking about is this. Pick any row or any column of the group table, and every element of the group appears in that row or that column exactly once. Let's pick this row. We have B, C, D, E, A. Every element appeared exactly once. Let's take this column, D, E, A, B, C. Every element appears exactly once in that row. In every row and in every column of this table, every element appears exactly once. That's not coincidence. And this is a simpler example. Pick any row of this table. Every element appears exactly once. Pick any column of this table. Every element appears exactly once. For example, let's pick the row headed by the element A. We see A, B, E. Okay, every element appears exactly once. Take the row headed by the element B. The entries are B, E, A. Every element appears exactly once. Let's look at the column headed by A. The elements that appear in this column are A, B, E. Every element appears exactly once. This is not coincidence. In a group table, every element of the group appears in every row and in every column exactly once. Now, I'm going to prove this, and I will do what may seem to be some unnecessary details in the proof. And I guess I'll explain ahead of time why I'm doing something that may seem unnecessary. And here's the fact of the matter. Originally, I said if G was a set with finitely many elements, then we could form a group table for the group G along with its binary operation. Well, you know what? If a group has infinitely many elements, like the integers under the operation of addition, that has a group table as well. It's just that we won't be able to exhibit all of the elements in the table. But the integers under addition, they have a group table. It's an infinite set. The integers is an infinite set, but the integers, along with the operation of addition, has a group table. So we can have a group table for a group that consists of a set of infinitely many elements along with a binary operation on that set. It is possible to have a group table. It's just we won't be able to fill the entire table. We won't be able to write out or display all the elements of the table since there are infinitely many. So the proof that I'm going to do that every element of a group must appear exactly once in every row of the group table and exactly once in every column of the group table allows for the fact that the group table could have more than one element. The group table could have infinitely many elements. And that's why I'm not going to take a shortcut that some of you will see that I could take if I were just restricting the size of the group to a finite number of elements. Okay, here's our theorem. Every element of a group G star appears in every row and in every column of the group table exactly once. So here's our proof. Let G along with the binary operation star be a group, and let X be an arbitrary element of G. So we'll show two things. One, X cannot appear more than once in any row or column of the group table. And two, X must appear at least once in every row and in every column of the group table. So first, X cannot appear more than once in any row or any column of the group table. We will show that X cannot appear more than once in any row. The proof for columns is analogous. So we're going to show that X cannot appear more than once in any row of the group table. The same proof will work for columns. Okay, the first part of our proof. We're going to show that X can't appear more than once in any row. And so we suppose, for the sake of deriving a contradiction, that X does appear more than once in a given row. Let's say that X appears twice in the row headed by the element G. So here's the row headed by the element G. And X appears twice in that row. So what that means is there exist elements A and B in G, such that in the row headed by G, this row, X appears in the columns headed by A and B. So here's the row headed by G, and X has to appear in at least two different columns, one headed by the element A and one headed by the element B. So what does this mean? The fact that X appears here implies that G star A is equal to X. And the fact that X appears here tells us let's see, this is G times B, or G star B. Now, where do we go from here? Well, remember, every element of the group has an inverse, such that when we multiply an element by its inverse, we get the identity element. So let's multiply both sides of these equations by the inverse of G. I'm going to multiply both sides of this equation by G inverse. And I'm going to multiply both sides of this equation by G inverse. Oh, and I wish I had more board space. I apologize. I'll tell you what. Just for the sake of making this more visually organized, I'll write what I had up here down here. So this means what? G times G star B equals X. And then I multiply both sides by the inverse. And now I can continue here and use associativity to associate these two elements together first. I'll do the same thing down here. I'll use associativity to associate these two elements together first. Star. Oh my goodness. Forgive me, this should be B. Yes. Okay, I think I got it right now. But what is G inverse star G? Isn't that the identity? So what that means is we have the identity star A equals G inverse star X. And that implies A equals G inverse star X. Well, that's not earth-shattering yet, but let's finish our computations down here. G inverse G is equal to E. So down here we have E star G equals G inverse star X. But E star G is just G. So that means Oh my goodness. Am I messing up here? Yes, I am. B, B, B. I beg your pardon. Oh, you're going to have to look at this proof again. I apologize. Well, what this tells us is B equals G inverse X. So A equals G inverse star X, but B equals G inverse star X. So this tells us that A and B are equal. Remember, every element of G appears exactly once as the header of a column and exactly once as the header of a row. Well, if A and B are equal, that means that this element appears twice as the header of a column. That can't happen.